Hello, welcome to Chapter 3 of Math 103 for Gilbert Community College. We're halfway through variable equations, which are, to remind everyone here, equations that involve variables, such as we commonly write them as letters, and constants, which are the numbers. Mix those together, solve for one or the other. That is what we're doing. We ended last lecture, in-person lecture, on this example here. The example here, of course, being solve this problem. And as we discussed previously, to refresh everyone's memory, the way we solve a problem like this is we want to make it so that it is all letters on one side and all numbers on the other side. This basic form here is essentially number equals answer. So if we look at this example here, we have letters on both sides of the equal sign, and then we have numbers on both sides of the equal sign. That's not what we want, so we need to change it somehow. And to change it, of course, we use our fundamentals of math, those being our basic operators: addition, subtraction, multiplication, division. As you get further along in math, of course, you're going to learn more and more and more and more and more math operators. But for this class, these are 4 that we really care about, right? So keeping in mind that addition, subtraction are opposite of each other and multiplication, division are opposite of each other, we utilize these to sort of cancel one another out. In the example shown here, let's say I want to move my x's to this side and my numbers to this side. I say, okay, I've got a 2x over here. I want that 2x moved over here. How do I do that? Well, I treat the parts of the equation with like terms. So if I, for example, subtract 2x from both sides, and as we talked about in class previously, if you do something one side, do the other side, these 2x's cancel, and then I have 5x minus 2x, which nets me a 3x. Now I'm in a situation where I have only x's where I want my x's, but I still have numbers, the 9 and the 3, that I want to get rid of. So this guy is this 9 here is subtraction. Opposite of subtraction is addition. If I add 9 to both sides, and again I have to add to both sides. When I do the one side, I do the other side, right? We've talked about this before. 9's cancel. 9 plus 3 is 12. 12 equals 3x. At this point, I have one number to get rid of, that being this 3 here. Oh, that's actually going to be back that up a bit. I don't want to take up space. Being that 3 there, opposite of multiplication, which is just 3 times x, is division. So if I want to get rid of multiply by 3, I divide by 3. When I divide by 3, the 3's blow up, giving me 4 equals x, which is what I'm looking for, which is my answer, right? We talked about this in depth in class before. I just real quick went through it, and we see that gracious corporate overlords at Cengage agree with us. Fantastic. Let's go over this one in depth. Let's go over this example in depth like we did in class previously, so we all have a good understanding of what's going on here. I suggest to you, if you're watching this on YouTube, to pause the video here, start working on the problem, and then play the video if you end up getting lost. With this live, if you're in here live with me, when I get to an example like this, write it down and start working on it. I'm usually going to do a little spiel like this to give you a chance to get ahead of me before I end up solving it myself, and then you can compare your answer to my answer. So 4x minus 5 equals 8x minus 7. Solve it. That means essentially solve for the unknown, solve for the variable, solve for the x. So I want this in the form of letters on one side of the equal sign, numbers on the other side of the equal sign. I'm going to, there's two ways I could do this, right? I could either move the 4x to the right or the 8x to the left. And as we've talked about in this class prior to this, those are both completely valid, but you usually want to be working in positives rather than working in negatives. It just kind of makes life easier. So I'm going to choose to move the 4x to the right. So I'm going to have all my letters on the right and all my numbers on the left there. I'm going to choose to do that because I can subtract. I'm going to rewrite the equation over here so I can work on it. 8x minus 7. Doing this because I can subtract 4x from both sides. Again, I write them in little t up top. That's how I personally do it. If you'd like to rewrite the complete sentence, go right ahead. Canceling the 4x's, pow, and landing me -5 equals 8x minus 7 minus 4x. I know when I have like terms, they can play with each other. So if I prefer instead, let me change that so that looks like a negative and not a whatever that was. I'm going to now rewrite this equation so that I clump my like terms together. 8x minus 4x minus 7. All my negatives are still correctly in place. So now that I have my x terms together, I can do the math solely around those. 8 minus 4 is 4. So minus 5 equals 4x minus 7. Fantastic. I have all my x's on the right. Now I just need all my numbers on the left, right? I keep following the same basic idea. If I see subtraction, I add, or I see addition, I subtract. I see a minus 7 here, which is a -7, essentially. So I'm going to add a +7 to both sides. It's kind of hard to write this teeny-tiny online, but I'll do what I can, right? When I add the 7s, they, again, blow up. Pow, bang, smash. I encourage you to make those noises. It makes math more fun. And then I have 7, +7, minus 5 equals 4x. 7 minus 5 is 2. 2 equals 4x. What I'm left to do here is I have 4 times x, which is multiplication. So I need to divide by 4 to get me there. Meaning I have 2 over 4 is equal to x. But I have a fraction that I know I can simplify. 2 over 4 is the same thing as 1 over 2. X equals 1/2 is the solution to this problem. I hope you got there as well. If you didn't, leave a comment down below. Tell me what happened. Or if you're in the live stream, say something, right? If you got questions, feel free to talk. Otherwise, I can just continue. All right, I'm going to clear this drawing now. And we will go forward and see if our corporate overlords at Cengage agree with us. The solution is 1/2. Fantastic. Again, I would like to point out, I move the 4x to the left. They move the 8x to the right for this example. Even though they moved the 8x, they still got the same basic question, just they were dividing by dividing negatives on top of each other. I was dividing positives on top of each other. Either way, we got the same answer. It really doesn't matter which one you do as long as you follow the steps correctly. All right, we got a new student joining. Hello, Luis. I give you a quick spiel before we get going. I am actively recording this right now. So if you have any questions, feel free to ask them, but they will be posted on YouTube. If you would like to ask me questions, but not on the YouTube video, then I'll have time at the end of this lecture. So it's up to you. I also look at the chat if you want to talk that way. So we just did another example of a big old fun variable problem. Now let's discuss solving equations that contain parentheses. When an equation contains parentheses, one of the steps in solving this equation is to use the distributive property. And essentially, the distributive property is used to remove the parentheses from the variable equation. Variable equations can be quite the hindrance. Sorry about that, hit my mic. Variable equations can be quite the hindrance in these, parentheses can be quite the hindrance in variable equations because you technically need to treat everything in the parenthesis as one unit. And dividing out and multiplying out like big equations within parentheses can be a hassle. We'll actually have examples of this later in class. So if you can not have a need for the parentheses, that makes your life a lot easier, right? When we discussed parentheses in previous chapters, we always solve the parentheses first. That way you can essentially work the equation without them. That's kind of what we want to do here as well. So I have this big stunking equation here. 4 plus 5 times the quantity. I got a pointer here. I should walk with it. 4 plus 5 times the quantity, 2x minus 3, is equal to 3 times the quantity, 4x minus 1. That's a lot going on there. There's parentheses, multiplication, addition, subtraction, sweet Lord. What do we do about this? Well, we still have the same end goal that we talked about prior. The end goal being, I would like this to be in the form of some letter is equal to some number. Once I get it in that organization, I'm good to go. But since this has parentheses, remember your order of operations, PEMDAS. There we go. In your order of operations, parentheses need to be solved before everything else, right? They're solved before everything else because they are everything in the parenthesis is treated as one object by everything outside the parenthesis. Treated as one object or thought of as one object. So when I have parentheses here, if I want to do something, I can't do something inside the parenthesis without doing something odd outside the parenthesis. I guess it's kind of the best way to put it. I can't just subtract 2 out of here because this 5 is working on the 2x. So how does that 5 affect that division of 2? And then this 4 is added to everything here. So if I divide a 2 out of here, how does that play with the 4? Likewise, how does that play with the 3? Do I divide the 3 by 2 as well? And then how does this 2 play with that 4 and that 5, right? It really gets out of hand very fast. You can work it that way, but just take my word, you don't want to. So what we do is, we've discussed this prior in class already, is we can use what's known as the distributive property. Meaning, we can understand what this 5 here, for example, means when it's being multiplied by the parentheses 2x minus 3. It means that 5 is multiplying here, and that 5 is multiplying here. Or in other words, I can distribute the 5 to everything inside. I can say this is the equivalent of 5 times 2x minus 5 times 3. And then I could put these essentially in their own separate parentheses. There we go. Kind of gross looking, but I hope you understand the concept. And then when I solve these individual parts, I no longer have need for that parenthesis. I have gotten rid of the point of having parentheses in the first place. So how does that work in practice? Well, let's just keep running on this. 5 times 2x. Well, what does that mean? When you have examples like this, you treat the, I don't want to go into the same detail I've been going previously with the expanding out of what does 2x mean. But essentially, you kind of work this the way we've been working previously, right? You treat the numbers as the numbers, and the letter just follows along. 5 times 2x is, let me get some arrows here. 5 times 2x is 10x. 5 times 3 is 15, so minus 15. This 5 times the parentheses becomes 10x minus 15. And I still have my 4 in front of there. But now I've rewritten the equation without parentheses. That looks familiar to what I've been doing prior. Likewise, I'm going to always suggest, until you don't need to anymore, throw those arrows in there. It just kind of reminds you of what you're doing. 3 times 4 is 12, so 3 times 4x is 12x. 3 times 1 is 3, so 3 times 1 is 3, and the negative carries along with it. Now that we are in this situation, this looks very familiar. I've ran into equations just like this guy. I know how to solve it. Right? And we go through our basic variable equation conversation for this. Let's start by, hey, I have like terms here, don't I? The 4 and the negative 15 are like terms. I'm going to rewrite the equation because it doesn't hurt to rewrite, it doesn't hurt to use your paper, where I clump plus 4 minus 15, clump my like terms together. I'm going to rewrite the entire equation to make sure I don't forget anything. There we go. 4 minus 15, that's weird, right? But we can do that in our head. 4 minus 15 is negative 11. Or if you can't do it in your head, pull out a calculator. So I'm going to rewrite my equation again as such. Sweet. Now I want all my letters on one side, all my numbers on the other side. Again, as with the previous example, we stop and think, okay, I can move the 10x to the left, to the right, or I can move the 12x to the left. Which one is better? Which one do I prefer to do? Well, if I move the 10x to the right, I'm going to end up with a positive amount of x's. I'm not going to have to deal with a negative that I don't want to deal with. So I'm going to try doing that. I'm going to subtract 10x for both sides. The 10x's blow up, pow, bang, smash. Oh, actually, I can do different colors, can't I? Yeah, I can. Yeah. Right, red for fire. Kapow, kabang, boom. And now I have 12x minus 10x, which is 2x. That negative sign is still there, so I keep the negative sign there. Now I've solved this far. Fantastic. Go team. I have a 3x. I want to move that over. Negative 3, opposite of that's positive 3. Fantastic. These two cancel. Let me change my color of my marker. Bang, smash. Landed me at negative 11 plus 3, which is negative 8. Negative 8 equals 2x. Lastly, divided by 2. I have x equals negative 8 over 2, which is the same thing as negative 4. Fantastic. We had to distribute first, which is an extra bump in the conversation, but it's not necessarily a difficult one. It's clustering your math and forcing you to solve things first, right? Again, that's the point of parentheses. Do this before you do anything else. Since there were parentheses in the original equation, we had to deal with them before we did everything else. They're doing their job, right? I'll clear these drawings. Unless anyone has a question. Clear these drawings. Go forward, and Cengage agrees with me. Yay! Woo! Yay! Woo! And what stamps do I have? I have hearts, text. That's all useless. No one likes that. Excellent. Let's continue. Here we have another example. There's a lot going on here. Work on this. Take your time. Pause the video if you're on YouTube. If you're live, start working on it right now. I'm actually going to take a quick break. I'm going to pause the recording so the recorded people don't see it, but I will be back. Okay, I'm back. So to solve this, we need to look at it, see what's going on, figure out our attack path, if you will, and then we'll attack it. I notice I have a variable equation, therefore I want this in the form of letter equals number. I don't know why I put 4 there. Let me move this thing out of the way. Oh, there we go. Oh, what happened? Yeah, whatever. Letter equals number. I noticed I have parentheses, so I need to distribute those parentheses out of existence before I do anything else. Okay, sweet. Let's do that. I notice I have a 4 outside of here, so I'm going to want to distribute the 4. Mouse, there we go. We're going to want to distribute the 4. And I have a 3 outside these parentheses, so I'm going to want to, again, distribute the 3. I'm going to draw my little arrows to make sure I do it correctly. I also notice this subtraction symbol. That subtraction symbol is a part of that 4. We need to not forget about that subtraction symbol. I'm going to treat this as plus -4. And I'm going to distribute -4 throughout. Because adding a negative and subtracting are the same thing. And this makes sure that I carry that subtraction symbol, carry that negative throughout everything I do. So let's start by distributing. 3x is not part of the distribution. So I'm going to, that's a terrible 3. 3x is not part of the distribution, so I'll leave that alone. And then I need to distribute -4 times 2, -8. -4 times -x would be positive 4x. What I did here is I wrote it as I answered it into a new sentence. I could have answered the just distribution. I could have, if I wanted to, like I did previously, write my distribution out here. I'll write it up here. -4 times -2. Oops, sorry. -4 times +2. There we go. Minus -4 times x. I could have written out that way and solved it through to my equation, but I just kind of followed my arrows as I was talking. Write that down, etc. And it gets the same conclusion. But just to be explicit, I'll do the other side of this, the full Monty. I'll do it up top here. 3 times x, 3 times x, minus 3 times 2. That is that equation. And then I have a -4 at the back of it. 3 times x is 3x. 3 times 2 is 6. There we go. Here, let me put that -4 a little closer just so it looks pretty. This became that, and this became that. Right? If it helps you to write out the expansion of the distribution and then solve it, please do. If you don't feel that's necessary, you don't have to. If you do it correctly, I'll be able to follow what's going on. And you'll be able to backtrack it as well, right? So I've distributed. I have completely removed all my parentheses. Now I have just a regular old solution. I notice I have like terms on both sides. So let me get rid of these guys so it's a little less gross. Oops. I notice I have like terms on both sides. I have a 3x and a 4x on the left. I have a -6 and -4 on the right. Let's solve those. Two approaches to solving that. First approach is to rewrite it as with the like terms clumped. like this, and then solve it. That'd be 7x. Ooh, that 7 is horrible. There we go. 7. Hey, that's a beautiful 7. 7x minus 8. Or I can, in this case, it is already clumped. So I can solve it and write down as I solve it. -6 minus 4 is -10. Now I'm in a situation like I did at the start of this chapter. Move my x's around, solve as need be. I'm going to keep my x's positive. So I'm going to move my the 3x over to the left. Minus 3x here, minus 3x there. Whatever I do to one side, I do to the other side. Change my color. The 3x's cancel. 7x minus 3x is that's what that's supposed to here. I'll write it out big just to make sure it's abundantly clear what's going on. There we go. 7x minus 3x is 4x minus 8. And those 3x's canceled. Minus 10. Then I will add 8 to both sides to get rid of these 8s. Again, I don't want yellow. There we go. My 8s cancel each other. Kapow, bang, smash, bang, smash, smash, smash. And minus 10 plus 8 is minus 2. So I am now at 4x equals -2. Opposite division is multiplication. Divide out. X equals, I'm just going to skip straight to the simplification because I know I can do that. When you're doing this work, you need to be explicit as is required for you as an individual homework doer, right? If you do not feel it necessary to, if you can look at 2 over 4 and realize that's 1 over 2, you don't need to show me that you did that change. You can just do it. Giving us with an answer of x equals -1/2. Hey, fantastic. Go team. Again, if you have any questions, leave them in the comments about what happened here and we can go over it. I'm going to clear my drawing now. And we'll see that Cengage is very happy with what I've done. We have pleased our corporate overlords. That is kind of the point of doing this, right? So, solving application problems using formulas. This is the word portion part of it. This is the part that always gets you. It's the part that always sucks to do. But it's the conversation you need to have because the real world doesn't give you an equation. The real world gives you a problem. And you need to derive the equation out of the problem. First one we're going to discuss is quite the problem, the fulcrum issue, the teeter-totter. Lever system is shown below, consists of a lever or bar, a fulcrum, that's the pivot point, and 2 forces, F1 and F2. Again, you're basically looking at teeter-totter here. The distance D represents the length of the lever. X represents the distance from each force. X represents the distance from force 1 to the fulcrum, and D minus X represents the distance from F2 to the fulcrum. Essentially, the X is how far you are away from the fulcrum. If the total distance here is, say, 10 meters, and you put the fulcrum 4 meters from F1, then over here would be 10 minus 4 would be 6, right? So here we do that. If this is 10 meters, and you place the fulcrum 4 meters from yourself, the other side is 6, right? Or 10 minus 4. You can equate these two together with the equation shown below. F1 times X equals F2 times the quantity D minus X. The benefit of doing this is you essentially can level the fulcrum. Since if it's directly in the center, if the fulcrum is directly in the center, say this is 10 and X is 5 here, this would be 10 minus 5, 5 over here. The equation at the bottom, let's draw a little arrow here. The equation at the bottom would then be F1 times 5 equals F2 times 5. Or the weights need to be equal on both sides, right? But if you skew the fulcrum to one side or the other, now you have a different conversation. As with the previous example, if this guy was 4 and 6, like I said before, then you would have 4 and 6. Meaning these forces would not have to be the same force to equal each other out. F1 would not equal F2. And you have different forces, therefore you need different weights to accomplish your goal, right? You guys know scales. You guys have seen levers before. It's not a new concept, but the math behind it is the important part. So I can give you this question. A lever is 15 foot long. A force of 50 pounds applied to one end of the lever and a force of 100 pounds applied to the other end. Where is the fulcrum located when the system is balanced? Again, the system is balanced when both sides equal each other. All right, what do I do here? Well, context clues, right? This equation is given just before it, so that equation is probably going to be useful. F1 x equals F2 times the quantity d minus x. I wrote it down in my notes. I'm going to, before I go any further, go back, make sure they're the same. F1x equals F2d minus x. Fantastic. Now I can go forward. So I have four variables, actually. I have an F1, an F2, a D, and an X. These are my, what did I just draw there? These are my knowns. These are the things that I need to either have knowledge of or I need to solve for. So what is what? Well, that's a good question, right? F1, F2 are the forces, but which force is which? Okay. I don't know, really. The question, the paragraph, doesn't tell you F1 equals 50 pounds, just says a force is equal to 50 pounds. Also tells you the lever is 15 foot long. Well, is D 15 foot or is X 15 foot? We need to know this, right? So let's go back to our information that was provided. The distance D represents the length of the lever. Okay. The lever is 15 foot long. D represents the length of the lever. D must be, I apparently suck at drawing with a mouse. D must represent 15. Cool. So one side of the fulcrum, the teeter-totter, has 50 pounds on it. The other side has 100 pounds on it. Which is which? Does it matter? I would argue no. It doesn't really matter which side you put the lever on because the fulcrum would just have to adjust accordingly, right? So let's call F1 50 and F2 100. Right? I can make this assumption and roll with it based on my inference I get from look at the question. That being said, if you look at this question, you don't know what the inference is, throw numbers in knowns and try it and see if your answer is stupid or not. If you get a stupid answer, well, maybe you did the knowns wrong, switch them around. If you don't get a stupid answer, well, that's reason to believe that you're probably correct. The slideshow suggests making a drawing. That's fine with me. They happen to choose F1 as 50 as well, right? Because F1 is associated with X and F2 is associated with D minus X. So they chose the same things we did. Ta-da! Cool. Now that I have my knowns, and I have my equation, I can fill in my equation with my knowns. Or I can just rewrite the equation with numbers in place of known letters. The x is still unknown, so I leave that unknown. And there we go. This is looking familiar now, right? I don't need that dot. I'll get rid of that. There we go. This is looking awfully familiar. I see variables, I see numbers, I have a variable equation. I need to just put it in the form of letter equals number, and then I have a solution. I also see parentheses, and I see a number outside those parentheses, distribution. I need to distribute this 100 throughout. So let's do that. I'll do this one long form again, just to make sure to emphasize what's going on. This is equal to 100 times 15 minus 100 times x. 100 times 15 is 1500. And now I am at this point. This brings up a very important point to emphasize, to state, if you will, about solving variable equations. You do not want to leave one side of your equality empty, ever. Because we'll get into this more later, but a lot of equations have more than one solution. A lot of times, 0 is an acceptable solution to an equation. And 0, a lot of times, isn't a useful solution to an equation. So setting a bunch of stuff equal to 0, for example, moving that 50x over, sometimes isn't very helpful. The other reason why you don't want to leave one side empty is you need something over there anyways. If I move my 50x over to the right, I'm going to have to move my 1500 over to the left anyways. So that's an extra step versus moving my 100x, adding 100x to both sides, moving my x over to the left, saving me the hassle than having to move the 1500 over there to compensate. Divide by 150. Give me x equals what, 10, I think? Give me x equals 10. Meaning on my 15-foot-long lever, I need to put the fulcrum 10 feet away from my 100-pound weight. That is what our math shows. So let's clear this drawing out and see if Sankage agrees with us. Hey, there we go. F2 is the X was the 100. Sorry, yeah. The fulcrum needs to be 10 foot away from the 50-pound weight. The reason I said 100-pound weight is because I forgot that we did a drawing. The drawing would have told us that X was on the 50-pound side, which is something I said before, right? But I forgot to recheck my work and just kind of ran along with it. X is 10, meaning this distance here is 10. This distance here is 5. And again, that's also kind of makes sense, right? That's how levers work. So we find the math itself seemed convoluted at first with a bunch of unknowns that weren't explicitly stated in our question. But if we take the time to work through them, hopefully figure out how to solve the problem, we will find this to be a lot less of a pain in the butt than we originally anticipated. Fantastic. Again, if you have any questions, comment them down below. Ask me in chat. Ask me in human live time, whatever you want to do. So, I think I have those backwards. Well, that's weird. Yeah, we just did 3.4, and now it's on 3.3. Well, I guess we'll do easier equations. My bad. We'll have to change that around the slideshow when I get around to it. Yeah, this is going to be going over stuff we've covered already, but it's good, more practice, right? It's a good thing. How to solve problems such as equations of the form x plus b equals c. To solve these, we keep using the exact same idea, right? We want this in the form of variable equals constant or letter equals number. To do this, I see I have the variable on the left here, which means I want my numbers on the right. To solve that, I'm going to first, usually you want to get as few numbers with letters as possible before you end up moving them. So in this case, I'm going to want to add 2 to get rid of this subtraction of 2. Now, you do the same thing to the left that you do to the right. Okay? You could make an argument for getting rid of the 3/4 first, but you want to do an issue wherein you need to multiply both sides by 3/4. And let me show you why that can be an issue. So I'll create the equation over here. 3/4x minus 2 equals negative 11. Let's say instead of doing the add 2, we want to instead multiply by 4/3. 4/3. We say anything we do to the left, we do to the right, correct? But what is happening with the equation as written? I need to treat the left and the right sides as their own operation. And by that I mean 3/4 x is not the entire thing that's on the left side of this equality sign. Minus 2 is also on the left side of the equality sign. Or another way to put it, this is all in parentheses. Same thing as technically, I guess you could say the minus 11 is in parentheses as well. So if I decide to give it a 3/4 first, I would need to distribute 4/3 throughout, giving me some x minus 8/3 equals negative 44/3. Right? And then, okay, this seems less than enjoyable at this point, right? I've randomly thrown fractions in here when I probably didn't need to throw fractions in here. And I've got dumb fractions too, 44/3. So it's a lot easier usually to get rid of all your addition and subtraction first. That way, you end up with a problem that has less fractions, less decimals, less things on intuitive. Cool? So let's blow up our 2's. Bang, smash, smash. Leaving us with 3/4 x equals negative 9. And then, now, when I multiply both sides by 4/3, I'm only affecting, I'm not having to distribute anything. I'm only affecting, really, one part of it. So x equals, what would that be? 36/3, which is 13. Negative 13. No, 12. Negative 12. Oh, geez. Oh, it's being recorded too. I'm so embarrassed. Negative 12. There we go. X equals negative 12. Sweet. Fantastic. Go team. Yeah. All right. This is stuff we've done already. Technically, this chapter should have came before the one we talked about. I have to rearrange this in the slideshow for, I guess, next time I teach. But it's still good to do these examples. Let me clear the drawing fast and skip on through the examples. Negative 9. Did I say negative 12? Ooh, yeah, that's bad math on my part. I apologize for that. Hopefully you caught my error. I am sorry about that. I'm having problems doing head math. Wait, no. I'm having problems skipping ahead. Okay, take a breather. I do math correctly. I am capable of knowing what I'm talking about. So, found the solution, went through the steps as we know them. Fantastic. You sometimes utilize these common multiples when you do this stuff. As stated in the slide here, it may be easier to solve an equation containing two or more fractions by multiplying each side of the equation by at least common multiple of the denominators. So the equation above, you can use 12, etc., etc., etc. Let's do our examples. Essentially, the idea was clearing denominators. Ooh, something in the chat. Yeah. I panicked for a second too, right? But hey, I was doing it correctly. Go me. So let's solve this. Again, I at this point, we've done these enough. You could probably run through it pretty fast and maybe won't need all the little tiddly little bits to be extra explained. I see a variable equation. I want letters on one side, numbers on the other side. Let's add 7. Give me 3x equals 2. Divide by 3. X equals 2 over 3. Huzzah, I'm done. I don't need to show any more work than this because it's very explicit, very apparent what I did. If you need to show more work, please show more work. If you don't need to show more work, hey, don't show more work. I'm not going to delete it. So I'm going to make sure I did it correctly. Yay! Woo! Yay! Go team. Go team math. All right. Application problems. We've covered equations like this before, right? Selling costs, markup costs, what have you. This slide is kind of cool because it's showing distribution of just variables to create equations that are useful. The cost plus the markup, as shown here, is how much something sells for, right? That's how stores work. When you go buy your bulk ramen for $4 for the pack of 12, Walmart didn't pay $4 for that pack of 12. Walmart paid $1 for that pack of 12, and they marked it up $3, so that's how much they made. The markup itself, however, is determined by some set rate multiplied by the cost of the product. So the cost is shared in these equations, and essentially what you can do, as shown down here, is you can write out these equations. It's supposed to be a C, not a parenthesis. There we go. Write out these equations as bundled versions of each other, right? Which is what's shown down here below. So instead of having two separate equations that kind of talk about the same thing, I can have one equation that talks about two things. Useful. And then again, we can use our equation to answer questions. The manager of a clothing store buys cross trainers. I don't know if those are a thing anymore. For $80 and sells them for $1.16. Find the markup rate. Again, I'm not asking for the markup, M, because the markup is just subtracting those two, 36. I'm asking for the markup rate. What percentage was applied to the cost of the shoe by the manager of the clothing store? Find the markup rate. We need to solve it. We know S stands for sell, so S is 116. We know C stands for cost, which was 80. And rate is what we're solving for. So we solve it, right? That equation looks very familiar to us. We can move on. Hey, look at that. I did it correctly. Go team. To solve it, here, let me get rid of what I drew down there. To solve it, we need to subtract the 80 out, because we want all letters on one side, all numbers on the other side, giving us, I think, 36, right? which was the markup. We essentially solved for the markup there. And then we are left with 80R, which case we divide by 80 to give us however the heck that is. What was it? 9 times 4 is 36, right? So it's 4, so 9 over 20, which is some percentage, equals our rate. That was head math. That's actually, I don't know if it's that correct. Let's find out. Yeah, 36 over 80 is 45%. Yeah, looks about right. Yeah, because 10 over 20 would be 50%. Yay! I did it correctly again. Woo! The markup rate is 45%. So the shoe store makes 45% on the selling point of the shoe. Cool. They converted this into a fraction right away because markup rates are percentages. That's why they did that. I left it as a fraction because head math. Go team. Markup rates, markdown rates, discounts, same concept, just it's subtraction involved. All right. We can go through this example again, where we have the sale price of something is $18.50. And then the rate, oh, sorry, I did that backwards, didn't I? Hey, thanks for catching me on that. The S is the sale price. The sale price is $14.80. Haha. See, I tried jumping the gun there, and I almost made a mistake. The regular price, the capital R, is $18.50. Why would we need to memorize the formulas? You don't need to memorize the formulas. These are just examples of when you're going to see this sort of stuff in the real world. No. These are all kind of the same formula. And as I've talked about before, I'm not someone who wants to push memorizing things that aren't actually beneficial to you. I want to say you are a health major. There's going to be things you're going to need to memorize for your degree. Markup and markdown rates on clothing are not one of those things. So if I give you a question that involves these, go look up the equation. That's fine with me. You don't, I mean, it's in the book. Open the book, Google it. Honestly, you could probably figure out these equations just by realizing these commonly known things here. The sale price is however much it costs minus the discount. The discount is some percentage of the price, right? So regular sells for $18.50. So this is $18.50 minus $18.50 times the rate. And then, well, yay, go me, I solved it correctly. And then we solve it. Shoo, spow, bang, smack. Right, move the 1850 over, divide out, 20% rate. Oh, you elementary education? Oh, my bad on that one. Elementary education might actually use these things. So if that's the case, then at some point you might have to have these things memorized. But you reach that block, you get there. I've never taught elementary school. I have no clue what formula requirements are required. My kid ain't old enough to be in elementary school yet. So she's working on telling us when her diaper is wet right now. She's math's a bit beyond her currently. In this class, we probably have a good understanding of these programs, so I'm going to run through these examples rather quickly. Of course, this talking I'm doing right now is time for you to look at these problems and try to solve them ahead of me. And then you can check your answer with what's going on at the end. So let's run through this guy. A necklace that's marked down 35% has a sale price of $292.50. Find the regular price. Marked down means we use this rate right here. Regular price is capital R. Sale price is S. Rate is rate. There we go. Or what says here in the givens, or as I like to say, the knowns. So let's solve that. Let's clear all that gunk out of the way. There we go. Sale price is $29,250, and that is equal to whatever the regular price is minus 35% of the original. Again, we do not use the percentage in math equations unless explicitly stated otherwise. We instead use the decimal version of the percent. 35% is 0.35. We take the decimal place, we jump it back twice, right? And once we have that, well, that looks like something I can solve, doesn't it? However, this one's interesting because I have two variables on the same side. What do I do about that? Well, we've talked about this already, right? That's like terms. But how do you subtract some number of R from R? The way you do that is you need to remember that this guy here is the equivalent of 1 times R. In your back of your head, that's one of them, and you're taking a little chunk of it off. So essentially, you're doing 1 minus 0.35, which is head math 65, 0.65 times the regular price. $292.50. So here, right, same song and dance we covered before. Since the 0.65 is multiplication, we need to divide. That is not math I'm doing in my head, but whatever that is gives us the regular price. Hey, hooray. So excited. And then we have Cengage do the math for us. Hey, that looks familiar. $450. The necklace originally cost $450, but the sale price of 35% off made the necklace cost $292.50. Makes sense, right? 35% off is a fair amount of money. That's a pretty decent sale. Oh boy, translating sentences into equations. This is the part that everyone always hates. If we're in class, this is the part where I make you tell me the sentence and I pour an excruciating detail out of you in the process. But you know what? This is online, so I'm going to have to digitally excruciate that process. The first and arguably most important operator, if you will, I don't know if it's even an operator, in math is, of course, the equal sign. What do you say to mean equal sign? What do you say to mean equality? Well, a couple obvious examples would be using the word equal. Equal means equal. But a simple is, what does is mean, right? Is can translate to an equal sign. This plus this is that. The is means the equal sign exists there. Amounts to, represents, comes to, all these other things translate to an equal sign. Knowing where the equal sign sits in your grammatical sentence makes writing your mathematical sentence 1,000 times easier. Example here, 5 less than number is 13. Cengage argues, I think it's a good approach, and I've talked about this before in class, to break down the important beats of the sentence to figure out what goes where. I see 13. That's a number 13. I see 5 less. 5 less than subtraction sign. A number, well, that's a variable. Let's call that n. And the important part here, the is means an equal sign. 5 less than a number is 13. So something equals 13. I know already my equation is going to be something equals 13. I have a 5, a negative, and an n left over. So my two approaches to solving this are I can either write them both down, which would be 5 minus n and n minus 5. And then I can look at those two. I can say, okay, those are my only two combinations. Which of those sounds like 5 less than a number? So if I am having issues in this particular example, context cluing the words out, I can always just solve it and figure out which one makes more sense. One of those two is going to give us was going to require a positive n. One of those two is going to require a negative n, right? That's a way we can approach this. Is that helpful? I don't know. It's kind of at the individual brain level, an individual way that you approach questions that's going to lead you to the correct solution. Me personally, I look at that 5 less than a number. So I have a number, I'm taking 5 away from it. To me, that sounds like n minus 5. But that's just the way my brain works, right? You need to do these sort of questions on the homework, on the extra credit examples in this slideshow here. You need to work these exact questions in order to better understand how to translate this stuff, because 5 minus n and n minus 5 are different. N minus 5. There you go. Now you know what n minus 5 is. You can, as shown there, solve it. So here we add the 5 over, getting us n equals 18. 5 less than, so what if we said instead of number, we say 18? 5 less than 18 is 13. Does that sentence make sense? 5 less than 18 is 13. To me, that sentence makes sense. 5 less than 18. Oh, I have a text thing. I'm going to type that out. 5 less than 18 is 13. If that sentence makes grammatical sense, then we probably did the equation correctly. The other version of that would have been, what was it? It was 5 minus n, right? 5 minus n equals 13. What's the other approach? Which we would have to, again, subtract the 5 over to give us negative n equals 8. There we go. So n equals negative 8. And then we would say the sentence would be, where's my text? There we go. The sentence in that case would be 5 less than negative 8 is 13. Of those two sentences, which one makes more sense? To me, 5 less than negative 8 is 13. There's an issue with that sentence. Namely, I'm at negative 8, I take 5 away from it, and I end up at a positive number. Well, that doesn't compete with me, right? So having the equation be n minus 5 works on all those fronts. Right? Again, I have to soak up that time I'd be expecting you to explain this to me in class with these convoluted explanations. But hopefully they're somewhat beneficial to you. We'll find out when I test you. Even odd integers, I'm sure you know what those are, right? Even integers divisible by 2, odd integers not divisible by 2. Is 0 an even integer? I don't know. All right, that's debatable. Oh boy, open subject in math. Phrases you can use. Consecutive integers is a phrase that you'll commonly hear. Consecutive integer, of course, would be integers that follow each other. 11, 12, 13 shown here. Those are consecutive because integers are whole numbers. Yeah, I mean, integers are non-decimal, non-fraction, rational numbers. 11, 12, and 13 are the closest you can get those numbers together. Negative 8, negative 7, negative 6 work in the same way. You will notice these both are ascending. That's commonly how they're written. I don't think you have to write consecutive integers as ascending, but that's just usually how it's shown. What this guy down here is the equation for consecutive integers. And of course, is a variable you can put any number into. And if you put any number into this equation down here, you will get consecutive integers. So let's say I want to call n as 6. Well, n plus 1 would be 7, n plus 2 would be 8. There you go, consecutive integers. If you have even consecutive integers, you need to add 2. If you have odd consecutive integers, you again need to add 2. But again, noteworthy, even odd integers follow the same equation. It just depends entirely on where you start. These consecutive integers swap even to odd. These stay all even or all odd, depending on where you started. Equations are still identical. Oh boy. Big, fat, fun little stack of words here. The sum of two numbers is 16. The difference between 4 times a smaller number and 2 is 2 more than twice the larger number. Find the two numbers. All right, let me check the time on this. I want to do this one in class. So we're gonna walk through this one in the live stream right now and in the YouTube video. If you take this class, I'm gonna probably hound you guys for like a good 45 minutes trying to figure this one out in person. If you know the answer from watching this, hey, I'm not going to be hounding you. Congratulations, those of you who watched this video. Let's do this. The sum of two numbers is 16. Well, that to me, summing is addition. Two numbers, those would be, two numbers. Let's call them N1 and N2. And the sum of those two numbers is 16. That to me looks a lot like N1 plus N2 is equal to 16. Is an equal sign. And 16 is, 16. 3. That was easy enough. But this last sentence is beyond that, isn't there? The difference between 4 times a smaller number and 2 is 2 more than twice the larger number. So, difference between 4 times smaller number, well, what is the smaller number? We don't know what the smaller number is. Does it matter? Well, not really. Let's just call N1 the small number. Or they call it N, same difference. That makes N2 the larger number. The difference between 4 times a smaller number and 2 is 2 more than twice the larger number. The difference is subtraction. 4 times, so that looks to me like I have a 4 and 1. The difference between 4 times smaller number and 2. So this and this have a difference involved between them. There's a difference between 4 times a smaller number and 2. So is that like that? I would take it that way. I would take it that way because grammatically it follows left to right, first of all. And secondly, I'm not given a reason to doubt the grammatical nature of that. And this is 2 more than twice the larger number. What does that mean? Well, again, is an equal sign. 2 more is usually plus. Sometimes they use it as multiplication. In this case, I believe they use it as addition. Then twice, 2 times the larger number, and 2. Is 2 more. So 2 plus 2 and 2. Is that what's going on here? It's tough, right? Notice in the example given, this is tough, right? This big stack of words is tough. I completely grant you that. But notice in the example here, they didn't use 2 different numbers, did they? They didn't do an N1 and N2, did they? They didn't do an N1 and N2 because this variable equation has 2 different variables in it. And something we haven't discussed until now, essentially, is that when you solve variable equations, you can only solve them if you have one unknown. Every equation we've had, when I write my list of knowns, always has one thing I need to solve it for. This is 2 things I need to solve it for. So what they did is they took this original equation here and they rewrote it in terms of each other. So they subtracted the N2 over. Sorry, they subtracted the N1 over, my bad. Because we say N2 is a large number. Subtract the N1 over. So that N2 is equal to 16 minus N1. So I can replace this N2 with this equation, netting me that bad dude right there. Let me get rid of all this stuff. Right? The reason why, so replace this with 16 minus N. Oh, that's a 2. My bad. Get over here, eraser. There we go. Minus N. Replace that in there, giving me 4 times N1 minus 2 equals 2 plus 2 times 16 minus N1. It was not wrong of us to think, since I have 2 different numbers, I should name them separately. But when we ran into the problem where I had 2 different numbers in one equation, I can't solve that. So I need to go back to my example and say, oh, if N1 plus N2 is 16, I have 2 equations, each with 2 variables, which, again, this is math that is something we'll talk about later, but we'll introduce it now. This textbook has a habit of doing that. But if the amount of equations I have is equivalent to the amount of variables I have, then I can solve the problem. Also, the amount of equations I have is greater than, I guess, the amount of variables. But I just need to reorganize all this information, right? And it is daunting. I completely agree with that. It is daunting upon first glance. But once you work it through and you realize how all these things come together, you end up with an equation, this guy here, or this guy here, that's very easy to solve, right? I can distribute the 2, giving me 4n minus 2 equals 16 times 2. 32? Yeah. 32 minus 2n plus 2. Like terms between the 32 and the 2. Excuse me. Sorry, sneeze there. So 4n minus 2 equals 34 minus 2n. I'm going to move my 2n over, add 2n to both sides. Give me 6n minus 2 equals 34. I'm going to add this 2 over to both sides. Again, moving stuff left, right as need be. 6n equals 32. Divide by 6. N equals 10. Right? No, n equals 6. 6 times 6 is 36. 5. N equals 5. There we go. No, 6 times 5 is 30. Oh my gosh. Is that right? 32 divided by 6. I should be able to do that in my head. I'm a terrible math teacher. 4. 6 times 4 is 24. 6 times 5 is 30. Did I do something wrong here? I love getting things screwed up on the live stream. Oh, okay. Yep. I see it. I see what I did wrong here. 34 plus 2 is not 32. 34 plus 2 is 36. See, I wrote plus 2 here, but for some reason the brain disconnected. There we go. 6 times 6 is 36. N equals 6. So then I have 6 plus N2 equals 16. N2 is 10. Small number is 6. Larger number is 10. There we go. Right? I got to make sure to check my work. If I run into things that don't make sense, yeah, 32 divided by 6 doesn't divide evenly. That would have had a decimal, and that seemed like a difficult answer for something like this, right? So, hey, good example of stopping and checking my work. Since I wrote my work down here, and here, since I wrote all this down in a way I could follow, I didn't try to cram it all together, I was able to catch my error, realizing this is addition, not subtraction. Giving me the spot where I can stop. I don't need to spend a lot of time staring at this, trying to recreate what happened. I don't need to go all the way back here and think maybe my equation at the beginning is wrong. Because I have shown my work, I know what I did. So let's clear this guy. There we go. Small number is 6, larger number is 10. Go team. We have successfully accomplished our goal. So I think that's going to end my live stream for today. Thanks for watching. I'm going to end the recording. If we have any questions, we can discuss those questions off camera if need be. But yeah, thanks for tuning in to the GoGibic chapter 3. This is, I think, like 3.3 through 3.5 or whatever. I'll look it up when I get done. And yeah, till next time.